I'm going to give a quick introduction to Dr. Rezende. She has a bachelor's degree in civil engineering from the Federal University of Goiás-Brazil and a master's and PhD in geotechnical engineering from the University of Brasilia. She has been an associate professor at the Federal University of Goiás since 2002, where she teaches and conducts research in civil engineering at the undergraduate level and geotechnics, structures, and construction in the graduate program. So she has conducted research projects supported by Petrobras and Brazilian and Goiás research agencies. Her research experience is in geotechnical engineering, which focuses on pavement, reuse of solid waste, tropical soils, and laboratory and field tests. So I think Dr. Rezende will talk about Brazilian research program, back in our home institution and some collaborative efforts she made in here with MATC. Right? All right, thanks, Dr. Rezende.
Thank you very much. Hello, everybody. So Dr. Kim have introduced me. I start talking with you about some research that we do in my home institution, Federal University of Goiás, and the study that we started here with Dr. Kim's group. Then I divide this presentation in three parts. First, I will present an overview about our research group from Brazil. Then I talk about a main project that you have there about the phosphogypsum study. And then I finished with the study that we started here with this partnership with UNL. First, I want to show where I'm from. This is the map of Brazil. And I'm from Goiânia. Goiânia is the capital of Goiás. It's in the Midwest of my country, as Nebraska is the Midwest here in US. And it's about 200 meters from Brasilia, the capital of Brazil. And we had about 2 meters. There we have some pictures from the city that you can see there. This is the timeline of our graduate program. So I have been a professor there since 2002. But our graduate program just started in 2007 in the master level for civil engineering. In this scope, we have geotechnical structure and construction. And in 2013, we have two important improvements in our infrastructure. We had the inauguration of the asphalt material and mixtures lab, with the financial support of Petrobras, and also the Technological Innovation Construction Lab with the financial support of FINEP. And recently, you got the approval to start the PhD level in our program for next year. And we are interested in a partnership with other universities. We wanted to start an academic network with University of Nebraska, Federal University of Goiás, Espírito Santo, and Rio de Janeiro. These are the professors that work in our group, in our program. In geotechnical engineering, you have 7 professors that work with geosynthetics, geomechanics, unsaturated soils, non-conventional materials for pavement, asphalt mixtures, chemical stabilization, tropical soils, and foundation. In structural engineering, you have 5 professors that work with structural concrete, steel fiber reinforced concrete, computational modeling, structural dynamics, and optimization. And in construction, we also have 5 professors that work with durability and performance of cementitious materials. Systems of mortar-based systems, waste, sustainable materials, durability of concrete structures, construction management, plumbing system, and water use. About the university infrastructure, we have, as here in University of Nebraska, you have 2 campuses. It's similar but it's not everything is the same. The evidence that you can see here is quite different than the evidence that you can see there. Here we see these beautiful squirrels, and there we can see monkeys around the campus. So this is our campus number 1. It's a little far from downtown. Here we have many courses, and the dean of the university works here. And in this green area that you have the monkeys. And here is the second campus that is close to downtown. All around this square, we have buildings of the university, and the School of Civil and Environmental Engineering is located here. And our program works in these buildings. So there we have 2 important labs. One of those is the geotechnical laboratory that is divided in 3 areas. The soil area, where we can perform tests for characterization soils, study tropical soils, compaction, CBR swelling, unconfined compression, direct shear, and compressibility tests. We have an area for unsaturated soils, where we can study suction and get another parameters with suction control. And the area for materials and mixtures characterization, where you can test aggregates, bituminum, work with Marshall and superpave mix design. And we also have this UTM machine, where you can perform the resilient modules, RDT, dynamic modules, flow number, and fatigue. There are some equipments for field tests that you can use to evaluate the performance of pavement structures in roads and highways, as compaction control, dynamic cone penetrometer, Bankman beam, sand patch, British pendle, and also to take a specimen core from the field. Now we are working on the rheometer acquisition by financial support of state and federal agencies, and also in the SCB test implementation. And this is the other lab that you have for the main studies here are applying materials in civil engineering as concrete, steel concrete, and we also have a room there for computational modeling of civil structures. When it's necessary, when we work with another labs, for example, X-ray diffraction and scan electronic microscopy can perform or in CRTI at UFG or furnace. And when you have to work with the rheometer or bind aging, we go to University of Brazil. And then, since I started to work there, we have been studying non-conventional materials for base and sub-base as clay laterite soils, greyways, construction demolition waste, phosphogypsum, and soil stabilization. And recently, we started to work with asphalt mixtures by laboratory and field analysis of cold-in-place recycling and HMA mix design and performance evaluation. So you are interested in a partnership with University of Nebraska. Maybe what you do with non-conventional material can be applied to new materials and techniques that the group work here. And we also want to improve our studies in HMA by applying FEM, SEM, and using multiscale laboratory tests. Then now I would like to show briefly to you one of the main projects that you have there. This project started about 12 years ago with the financial support of state and federal agency, and also the company that produced this material. So what is phosphogypsum? It's a product that you can find in phosphate fertilizer industry, because this kind of company wants to produce fertilizer to use in agriculture, But during this process, we have the exploitation of the phosphate rock and the addition of sulfuric acid to get the phosphoric acid necessary to get the fertilizer. But in this phase, we also have the production of a waste that we call phosphogypsum. And the problem is that for each ton of phosphoric acid that we produce, we have about 5 tons of phosphogypsum generated. And the problem is that material is laid up in open piles or stacks. It occurs in Brazil, Goiás, and also here, for example, in Florida. And it can have some problems about this kind of dispose related to environmental concerns. For example, in Florida, the numbers show about 1 billion tons stacked in 24 piles, and 30 million new tons are generated each year. Then you can think about how to use this material. You can use this material in engineering purpose, but you have to take care about the environmental risks because of the impurities that can appear depending on the origin rock and the process of the beneficiation that happens in the industry. So you can find heavy metals and radioactive elements in this material. In the case of the Brazilian phosphogypsum, we observed no problem with radioactive levels and no health or environmental risk. But some solubility tests showed problems with aluminum and fluoride concentrations. Then we started to study this material in 2006. We think about to use phosphogypsum to stabilize soils. So the phosphogypsum that you have there is the dehydrate type. And the soil that we have more abundant is the clay tropical soil. Then we performed the lab and field tests. By lab, we found that this dosage is a good start to get better mechanical behavior. And we use this mixture to construct a low volume road and use this in the base. Since this construction, we have been monitoring this pavement with field tests. But in that time, we found a problem. When you put this material in contact with water, it happens, this thing happened, and we started to figure out why it occurred. And then we performed X-ray diffraction tests and observed the formation of etringueira, a mineral that can cause swelling. And for the use as subbase and base materials, you don't want this. Then, in the next phase of this study, we think about to transform the dehydrated phosphogypsum by a thermal treatment in the hemi-hydrated type, trying to solve this problem about the swelling. And then we add also cement and lime, trying to improve the mechanical behavior. Then the main results of this work is presented in this paper, and I will summarize briefly in the next slides. We work with 10 samples, soil mixed with lime, and other 8 mixtures where you change the type of phosphogypsum, and also sometimes you have soil, and other samples you don't have soil. Then we perform the lab tests, characterization, compaction, mechanical tests, and to complement the results, we performed X-ray diffraction and stunning electronic microscope tests. These are results for swelling tests. It's a Brazilian specification where we put the sample in contact with water during a period and observe the volumetric strain. these results showed that mixtures with the H type, we have high values for volumetric strength, but for mixtures with hemihydrate type of phosphogypsum, you have low values. So it's a good result, showing that the transformation of the DH into the HH can work. And then this is a result for unconfined compression test. And you can see that these mixtures with HH present good results. And when I have the dehydrate type, maybe with the soil, you can get some good values for the strength too. And about the resilient modulus, we got for the mixtures with the hemihydrate type, we got good values too. And these values are higher than those that you observe for traditional materials that you use there for subbase and base of flexible pavements. So it's possible by mechanical tests, these results show that it's possible to use these mixtures. Then you can see that with the swelling and mechanical tests, the dehydrate type present the worst behavior. Maybe it's not good to use for this purpose. But when you transform for the hemihydrate type, you got the best behavior. And mixtures with this material with lateritic clay presented intermediate behavior. But by now, we cannot explain why this difference of behavior occurs. For this, it's important to take a look in X-ray tests and SEM images. By the X-ray tests, we observed that in the H mixtures, we still have the etringueira, what we don't want. But when we use the hemihydrate type, we observe etringueira only in the mixture cement. For lime, we didn't note it. And also, when we take a look in the images from microscope, we observed first that the shape of the dehydrate type is different from the shape for the hemihydrate type. Here we have tabular, large plates, and because of these more porous. And here we have small lamellar plates with less porous, which can impact in a good behavior because of this microstructure. For the mixtures, we observed with the DH that the etringueira appears, but in different morphologies. In the mixture cement, we saw greater lengths, and in the mixture with lime, we saw small radial and crystal spheres. And when you see these mixtures with hemihydrate type, we didn't observe the etringueira. And the mixtures with soil, we here with the dehydrate type, we see etringueira together with the phosphogypsum plate. With the hemihydrate, we cannot see it. And also here we can see agglomerations because of the chemical reactions. Here these agglomerations are bigger than here, it's smaller. So here we can see a more homogeneous microstructure. And that you believe that because of this, you have better behavior, mechanical behavior here than here. Then with this study, we conclude that the DH type present limitations because of the presence of etringueira in the porous structure. DH maybe can be used if we combine with lateritic soil and stabilizer, but in low content. And the thermal treatment works. We got better results using hemihydrate type of phosphogypsum. And with this material, you can think about use more of this byproduct, what is a good point. And then this year, we had another paper related to this topic, but the focus here is to apply this material for embankments. And then we present results of shear tests and compressibility tests. And we also are in the process of re-review of this paper for the Resource Conservation and Recycling Journal. You think there are many things that you can do in this area. For example, study performed SCB tests with this material. We're talking about to start something in this way in the next year, but maybe use this material for hot mix asphalt and also in gel polymers. And now I want to show the main results that we observed in the study that I start here with Dr. King's group. First, I think it's interesting to present why I decided to come here. Then I met Dr. King for the first time in a conference in Brazil, in the south of Brazil, Cataratas. It's a beautiful place to visit. It was in 2015, and I was in this presentation about binder specifications towards sustainable pavements. And then I was interested to start to study something this way. Since then, I was looking for a scholarship to be here, and finally, in the end of last year, I got the Fulbright scholarship to come here during this fall. And why I want to study hot mix asphalt? It's because, unfortunately, in my city, I see these every day. So we see several problems with rutting and cracking. So I think it's important to improve our pavements. And in terms of fatigue, we can work in lab using many scales, trying to predict what will happen in the field. It's common to work in the binder scale by performing tests in the rheometer or doing many tests with more in real scales with the asphalt concrete samples. But when we see the results for the binder test, we can note some problems because of the difference that exists between the film thickness in this test and the real film thickness that exists in the asphalt concrete. And in the other scale, you have good results, but it's time consuming, it's hard to get the samples, and the analysis can be complex. Then we can try to work in an intermediate scale. Many studies have shown that it's possible to work with them to predict this mechanical behavior. And then we can work with the rheometer to get the complex models and the phase angle with less time, with good repeatability, and use the cylindrical samples. However, there are some shortcomings. For example, about the sample productions, it's sometimes not easy to get the samples in the asphalt concrete. And also the fine aggregate will impact, that we use these mixtures, will impact the results. So it can change depending on the mixture that you are working. Then we think about how to get better fatigue parameters for asphalt binders. And with this experience of the FAM, we are trying to use the rheometer and the cylindrical samples, but work with the sand asphalt mortar. There are some papers that present results of these studies. These papers show that sand samples are easy to produce, successfully evaluate fatigue characteristics. Time sweep tests presented reasonable fatigue failure point with good repeatability. Then, based in the methodology that will be presented by Santosh and Dr. Kim the next IB, we decide to work with a standard sand that you can find everywhere, mixed with the binder that you want to study, and put into this mold. This is a special mold, and compacting this penetrometer in a fixed energy. Then, after this process, you can open the mold and get the same sample. In this period, we work with one binder type, the PG64-34. We vary the binder content in 6, 8, and 10%, and the geometry in terms of high in 50, 40, and 30 millimeters. We perform tests on the rheometer, and you are interested to find the relation between the complex models, phase angle, and the strain. So we perform the strain sweep tests where the frequencies were fixed in 10 Hertz, and the percentage of strain vary in this range. We also vary the temperature for the tests in 10, 25, and 45 degrees Celsius. So for each configuration, we work with at least 4 tests, trying to check the repeatability of this methodology. We also try to figure out the film thickness using 2 procedures, estimation by equations and images with the laser scanning microscope. This is an example of the results that you get. This is for 8% of dosage in 3 temperatures and also in the 3 geometries. So you can see the relation between the parameters, complex models, phase angle, and strain. We can see the failure point in all tests. And you also can see the influence of the temperature, because depending on the temperature, we got different shapes for these curves. We just finished this test, but now we will start to analyze the results. And we think about to get these 5 points for each curve. The initial complex models, the strain, where you have the behavior changing here in the curve, the initial phase angle, the phase angle for failure, and the strain for failure. And so the plan is to check the variability of these parameters for each situation: temperature, geometry, and binding content, to figure out if we are having good repeatability with these tests. These are some examples of the failure because of the test. We get this in the samples. Sometimes we see the failure here with cracks in the middle. Most of the time it's in the middle of the samples, but sometimes you can see close to the bottom or even close to the top of the sample. And about the film thickness, this is the results for the estimation. So you believe that we are in this range, about 9 and 50 micrometers. And we suppose that with this, we are close to the real in the field. And with the laser microscope images, you can see the aggregates and the space between the aggregates with the binder. Then we can get this distance and consider that the film thickness for each aggregate is the half of this distance. Then you can get numbers about 10 and 28 micrometers, and they are close of the estimation. And also, we believe that they are in the range that you want, want to work in this study. So we will finish this analysis. We will prepare a paper with these results. I will come back next week for Brazil. Then I want to replicate this methodology there using the same sand, the same test, but with another binder, the binder that you have there. And we can do another. We think about do another tests in the rheometer and the future work with just asphalt binder and continue this study there. Then now I would like to thank you for this amazing opportunity. University of Nebraska, the Mid-America Transportation Center, and Fulbright and my home institution that support me during this month. And also I'd like to wish you Merry Christmas. This is a tree that my students prepare in Brazil in the lab. They used asphalt samples that they work in their tests there to produce this tree. It's here is Feliz Natal, Merry Christmas in Portuguese. And thank you very much for your attention.
So, any questions from audience for Dr. Rezende?
Come on, guys.
I have a question about your phosphogypsum study. You showed that the resilient modulus were very high comparative with typical materials that are used in vase. But with that high resilient modulus, don't you expect problems like with reflective cracking, for example, from the base to the...
Yes, you can.
You are monitoring the load, right?
Yeah. But the first trial that you work was with the dehydrate type. Mm-hmm. So we don't expect this, but for the hemidryate type, because of the higher values, it's possible. So when you use it in the field, you have to think about how to block these cracks, as we do with cementitious materials. Yes. So.
Other questions?
Yes, the Atrin guide comes from where?
Sorry?
The Atrin guide, you show it in there.
It's okay. We believe in the mix with the cement. We believe it's because of the reactions that you have there, the cementitious reactions. But when you don't have the cement, we have only the phosphogypsum. It's because of the material, the shape of the material and the elements that you have there in the reaction between phosphogypsum and soil. The elements of the lateritic soil, because it's a tropical soil, so you have aluminum and other things, and the products from the phosphogypsum.
So in the STM images, you just understood the presence of the etrigite because of the shape, or you did some kind of...
Both. It's the shape and the reactions.
Any others? About your sand asphalt mortar, you use Arwa sand, right? Mm-hmm. Why not the beach sand in Brazil, Copacabana?
Because okay.
So, Dr. Rezende will come back for sure, and we will continue to work with her in Brazil. She will be a good ambassador for us in Brazil. So we work together as very close relationship. Thanks for choosing us again. Thanks for your time with us. And this is from director, not from me. It's director of MATC, Dr. Lilian Rezende. He couldn't make today, but small souvenir for you.
Thank you very much, Dr. Kim. Thank you.